Hello everyone, my name is Fabio Le Piane, I am a PhD student from Bologna, Italy, and I work at the local CNR-ISMN headquarters, and in particular I am part of DAIMON, which stands for Design and Integrated Modeling of Nanostructures. Here we present our first work of a new research activity, which will lead us on an impervious road to mix classical simulation workflows with machine learning and data science techniques. In particular, we try to develop a system that can predict properties of a molecule pair extracted from a bulk of molecular material whose properties have been calculated via ab initio calculations like DFT, molecular dynamics, and so on. As you can see here, we depicted the classical multiscale simulation and data workflow, and here you can see how we would like to modify it in order to exploit machine learning. In particular, we try to overcome the computational bottleneck related to the computation of a target properties for each pair in a bulk. And while traditional simulations may take more than 40 minutes for a single pair, a machine learning models, once trained, can approximate the value of the same properties in a matter of milliseconds. In this specific case, we tried to train a model able to efficiently compute the electronic coupling of a pair of DPBIC molecules, which is a molecule suited for OLEDs. We studied many different approaches with regard to featurization of the molecule pair. For example, we represented them as a triplet of distance, quaternion, and distortion, or as a pair of a distance and Coulomb matrix. And many different machine learning algorithms, in particular random forest, kernel ridge regression, and gradient boosting. As you can see in this graph here, we get a model which can fairly correctly predict the trend of the electronic coupling, exploiting in particular a gradient boosting regressor. These results have been obtained through a Python stack, in particular using the well-established scikit-learn library. We faced the also well-known limitations of the entire Python ecosystem for science, where the actual computation is led from a C library and where Python is just a simple front-end. This kind of setting is a setting where the actual implementation of the methods is masked to the final user, making customization and improvement more complicated. In order to overcome such limitations, we start to experiment with different languages and their respective stacks, and in particular we focused on Julia, because of the easy implementation, similar to Python being an interpreted language, paired with incredible performance, and Rust, which is for its new view on system programming languages and their relative performance, of course. Our future works, we use these results as a base to start experimenting more with these new programming stacks. Moreover, we would like to implement a deep learning-based approach in order to find out how good our featurization is and to see if we could actually exploit a neural network to generate a more general encoding for the application of machine learning-based technologies to material science. Thank you for watching this pitch video. Bye.